Welcome to lecture number 31 for ECE 341 Random Processes. In this lecture, we're going to look at an F test and a type of F test called analysis of variance. Now, so far we've looked at a t-test, chi-square test. Here's a third test, F test. T-test is a test of a mean. Chi-square test is a test of a distribution. And F test is a test of the variance of two distributions. Now this is useful for a couple of reasons. In manufacturing, one indication that a manufacturing process is about to go out of control, i.e. fail, is the variance of the output starts to increase. And you want to know that because I actually want to predict before the assembly line goes down. If an assembly line goes down, that could be millions of dollars every day. I would like to repair the assembly line before it fails so I can keep it in production. That's important. That's worth millions of dollars. It's useful in stock market analysis. A similar theory holds that an increased volatility in the stock market is an indicator of an upcoming recession or a crash. Again, if you can predict the future, you can make a lot of money in the stock market or avoid losses. It's also used in comparing the means of three or more populations. For example, a t-test that we looked at before is only good for one population. I can manipulate it to work for two populations. It doesn't really work for three. Analysis of variance is a way to analyze the means for three or more populations. So let's kind of back up a little bit. There's a couple ways to estimate parameters about a population. One of them is the mean. If I assume X has a normal distribution, then one way to estimate the mean is to take the average of your data. That average will have a normal distribution with a mean of the population's mean and the variance of the population's variance divided by n. So it looks like 1 over n is kind of saying as the population sample size goes to infinity, I eventually know the population's mean precisely. That's a normal distribution. If I estimate the population's variance, that's this calculation, the distance to the mean's population's mean, or distance to the sample's mean squared divided by n minus 1, that has a gamma distribution. Again, it kind of looks like this. Typical for gamma, I can't go negative. If I take the ratio of a normal distribution to a gamma distribution, I get a student t distribution. That's what we did the last couple lectures. If I take the ratio of two gamma distributions, I wind up with this lecture, an F distribution. It's an F distribution with n minus 1 degrees of freedom in the numerator, n minus 1 degrees of freedom in the denominator, and the F score being the ratio of the two variances. Now essentially, an F distribution is used when you want to compare the variance of two populations. And the way an F test works is, for example, suppose X is a random variable with unknown mean, unknown variance, and m observations. Y is a random variable with unknown mean and variance and n observations. The hypothesis is the variances are different. The procedure is to first compute the variances of the two populations, then calculate a new variable f that's the ratio of the two. And f is always greater than 1, so if the variance of x is less than y, you flip it. Once I have the f score, I can convert that to a probability by using an f table. Now, f table will look something like this. If I have a alpha level of 0.1, meaning I can be 90% certain that the variances are different, it looks like this. The top would be the numerator's degrees of freedom. The left-hand side is the denominator degrees of freedom. The number in the middle is the F score. So suppose I have a sample size of 5, meaning 4 degrees of freedom in the numerator, and 6, meaning 5 degrees of freedom in the denominator. I'll look for this number. If the ratio of the variances is more than 3.52, I can conclude that the variances are different with a probability of 0.9. That's kind of an F table. So for example, suppose x and y are normally distributed. X has a mean of 50, variance 20, or standard deviation 20. Y is a normal distribution, mean of 100, standard deviation of 30. Let's take 5 samples from x, 11 samples from y. My null hypothesis is that the variance of y is more than the variance of x. So the first step is you take some measurements. Suppose I had these 5 measurements from x. I've got these 11 measurements from y. Once I have the data, I'll find the variance of x, find the variance of y, take the ratio, I get an F-score. Now if the F-score is less than 1, I flip it. F-scores are always bigger than 1. I have an F-score of 2.82. Now what I do with that is I go back to my F table. I had 10 degrees of freedom in the numerator, sample size 11. I have 4 degrees of freedom in the denominator, sample size of 5. Here's the number that I'm looking for, 3.92. If the F-score was greater than 3.92, I can conclude with 90% probability that the variances are different. I don't have that, so I can't make any conclusion with a 90% confidence level. That's basically an F test. Second way is go to StatTrack. And StatTrack is like everything. Go to StatTrack, input the numerator's degrees of freedom, denominator's degrees of freedom, the F value, and it kicks out the probability. That tells me that I'm 84% certain that the two populations have different variance. So that's basically an F test. Where you would use this? Well, one application would be like the stock market. The stock market goes up and down. It's got some variability. One indication that the stock market is in trouble is if the variance goes up. So let's do that. Let's compare 2 different years. Stock market in 2010 and stock market in 2021. Now here's what the data was. If I normalize it so that the starting value is always at 100, there's how the stock prices varied each year. Is the stock market getting more variable? Meaning that I would start to worry that maybe the stock market is going to crash. Well, to do that, I would take some data. I've got the year 2010, 2021, the mean, standard deviation, number of data points. Take the F-score, that's the ratio in the 2 standard deviations, put the larger number in the numerator. I get 12.4. 249 degrees of freedom in the numerator, 250 in the denominator. Probability that the variances are different is 1. So my conclusion is that I'm almost certain that the stock market is more variable than it was 11 years before. So it's ready for a crash. That's one way to analyze it. This probably isn't a fair comparison though, because the mean in 2021 was almost triple what it was back in 2010. So if the variance is 3 times bigger, maybe that just means that the amplitude is 3 times higher. So another way to analyze it, let's normalize it. Let's start every year at 100, or at 1. Find the standard deviation for the normalized data, in which case the standard deviation goes from 0.395 to 0.441. Take the F-score, now it's only 1.24. Go to StatTrack and put 1.24 with those degrees of freedom. I get 94%. So let's show you how that works. We go to StatTrack, go down here, a bunch of different distributions, F distribution. StatTrack has like everything. Go to your F table. I have, what was it, 249, 250, 249 degrees of freedom in the numerator, 250 degrees of freedom in the denominator. My F-score was 1.2465. 1.2465. Calculate. 95.9%. That's StatTrack. So again, it looks like the stock market is in trouble. Well, if you recall, the stock market didn't crash after 2021. So something's wrong with our analysis. Here's another way to look at it. If you look at the stock prices, there is an overall downward trend. When you do analysis, like the variance, it doesn't care whether the data was doing a nice straight line like this, very well behaved, or is completely erratic, doing stuff like this. I get the same variance. One way to take that into account is let's do a linear curve fit. Let's do a linear curve fit for 2021, linear curve fit for 2010, subtract out that line, and we'll have the deviation relative to that curve fit. So I'm looking at the blue line relative to a straight line. Is that more variable? So if I do that, I've done a linear curve fit. The mean from your straight line approximation is 0, kind of by definition. The standard deviation goes from 0.03 to 0.02. The F-score is 2.7. But in this case, the larger one is 2010 versus 2021. The variation went down, which tells me the stock market is just fine. So what is the right answer? Is the stock market going up? Is it going down? Well, it depends upon how you analyze it. This is actually in the past, so I know that the stock market didn't crash in 2022 or 23. So it looks like maybe the last way was the correct way to analyze it. That's part of the challenge being a stock analyst. It's not exactly clear how you analyze the data. There's a couple ways, but for any of those approaches, I can analyze it using an F test to tell you is the data more variable or less variable. That's kind of what an F test is. Some other things you can do in an F test is if you have a bunch of, say, transistors from 2 different vendors, I can find the variance of each population and see, are they different? Might tell you if there's different manufacturing process, different day, different manufacturer. Things that an F test can tell you. Are the variances different? So that's an F test, measure of the variance. That leads to another topic, analysis of variance, also called ANOVA. So a second use of the F distribution is when you want to compare the means of 3 or more populations. Now, what we did before is a t-test. A t-test works for a single population. If I have 2 populations, I can create a new variable w that's a minus b, and then compare a versus b. By doing a minus b, I now have 1 population. T-tests work for 1 population. What do I do if I have 3 or more populations? Well, this is where analysis of variance comes in. Now, the basic idea, if I have 3 populations, I've got a mean for A, B, and C. I've got the variance for A, variance for B, variance for C. I also have the global mean and a global variance. Now, if the global variance is bigger than the individual variances added together, that kind of tells you I have 3 distinct populations. If the global variance is basically the same as the individual variances added, it's the same population. That's the idea behind analysis of variance. And what you do is I create 2 numbers, the mean sum squared between columns, between data sets, and mean sum squared within data sets. I'll have the mean sum squared between data sets is what is the variance relative to the global mean? How much does A vary versus the global mean? How much does B vary versus the global mean? And C. That's the numerator. The denominator is how much each data set varies relative to its own mean. So it'll be A's variance, B's variance, C's variance. Add those up. I get the mean sum squared within columns, within data sets. Take the ratio, I get the F-score. Now an F-score close to 1 means basically the 3 means are the same, and F-score much different than 1 means at least one of the data sets is different. meaning one of the means is different, it was a different population. So that's kind of the idea. The equations for analysis of variance use a bunch of variables. These are defined as follows. K is the number of data sets, 3 in the previous case. Little a sub I, b sub I, c sub I are samples from each data set. A bar, b bar, c bar are the average of each data set. NA, NB, and C are the number of data points within each data set. S squared A, B, and C are the variances of each data set. Capital N is the total number of data points. Capital G bar is the global average, and S squared sub G is the global variance. So here's how the calculations go. The mean sum between columns is defined as follows. You've got your 3 data sets. So let's do the calculations for the numerator and denominator. In the numerator, I want to find the mean sum squared between columns. So what I'm doing is I want to know, I've got population A, B, and C. What is the variance relative to the global mean? Now this is kind of why my personal opinion is this calculation is incorrect, and they'll show up a little bit later. The correct way, in my opinion, to do this is you find the global variance. If you have all the data, what's the variance of A, B, and C lumped together as one giant population, which would be each data point in A relative to the global mean, plus each data point in B relative to the global mean squared, plus each data point in C relative to the global mean squared. So what's that distance? Add them all up. That's mean sum squared between columns, also known as the global variance. That's not how it's done, though. The way it's actually done is I have the average of A, average of B, average of C. I'm going to approximate that the sum of A sub I minus G squared, that's almost the same thing as the sum, well, there's just one point, as the number of data points times A bar minus G bar squared. Now that's not exactly true. Squaring is not a linear function. So when I add up these points relative to the global mean, I'll get a different answer than this one. So in my opinion, this is the incorrect way to do it. However, this is how you do analysis of variance. If you don't follow this procedure, you get answers that are different than everyone else in the world. So the standard way to do it is you don't do the actual variance, you approximate it with the distance from A bar to G bar squared times the number of data points in A, and that'd be the sum of AI minus G squared, roughly. Not exact, but rough. Likewise for B, likewise for C. Add them all up, and then divide by number of data sets minus 1. In this case, the numerator has k minus 1 degrees of freedom, so if I have 3 data sets, I have 2 degrees of freedom. The mean sum squared within columns is just the sum of each data point relative to its mean squared, likewise for B and C. Note that this sum is actually the variance of A times the sample size of A minus 1, because the variance is just this divided by NA minus 1. So if I multiply by that, that clears out the denominator, and I get that summation. So either one's the same. Likewise for B, likewise for C. Once I have that, find the overall average. In this case, I divide by number of data points minus number of columns. And this has n minus k degrees of freedom. So if we have 3 data sets and 100 points, that'd be 97 degrees of freedom. The F test, F score then, is the ratio of the numerator to denominator, mean sum between columns to mean sum within columns. If the F score is large, then I can reject the null hypothesis that the means are the same. If it's small, then it basically means all three are from the same population. So for example, let's take this data set. I've got population A, B, and C, 10 measurements from A, B, and C. Do the three populations have the same mean? If I look at it, I can tell pretty much they don't. I can also see that here's the mean of A, mean of B, mean of C. Does that show up with an F test? So to do that, I have to calculate the mean sum squared between columns, mean sum squared within columns. Those are the calculations. In MATLAB, I can do that. Input the data, A, B, and C, find the length of A, B, and C, the total number of data points, and 3 columns, 3 data sets. The global average is just the average of A, B, and C taken all together, is 20.86. Mean sum between columns is the mean of A minus G, that distance squared, times sample size of A. Mean of B minus G, global mean, squared, times sample size of B, likewise for C. Add that all up, I get 21. Next, calculate the mean sum squared within columns. So what I could do is the distance of each data point relative to A's mean squared, plus the sum of the distance from each data point in B relative to its mean. Again, this is my data set, so this actually has a bunch of points. Take all those added together, likewise for C, divided by total number of data points minus number of columns, I get 3.02. That's one way to calculate mean sum within columns. That's the correct way of doing it. In my opinion, that's really what you should have done in the numerator, but that's not what's standard. Equivalent. I can take the variance of A times n minus 1 plus the variance of B times n minus 1 plus variance of C times n minus 1 divided by n minus k. I get the same answer. So either calculation is correct. 2 different ways of doing the same thing. The F score then is the ratio of mean sum between columns to mean sum within columns. I get 7.25. Once I get that, I go to a T or F table or a stat track. The numerator has k minus 1 degrees of freedom. Denominator has n minus k degrees of freedom. My F score is 7.25. The probability then is 0.996. So 99.6% certain that these populations have different means. At least one of them has a mean that's different. It doesn't tell me which one it is. I would need to use a t-test to find out which one that is. But this tells me, I'm pretty sure these are not from the same population. In MATLAB, I can do these calculations as follow. I generate my data for A, B, and C, calculate the mean of A, variance of A, mean of B, variance of C, and so on. Total number of data points for A, B, and C. Global total number of data points. Here's the global average, mean sum between columns, mean sum within columns, F score. All the calculations in one script. That's one way to do an F test. If you're familiar with MATLAB, I would just use these calculations, just change A, B, and C, and just run with it. Another way is to use an analysis of variance table. This is what that looks like. I've got my data set for A, B, and C. What I do then is, given the data, I calculate the mean of A, mean of B, mean of C. Given all the data, I then find the global mean, G. Number of data points for A, B, and C. Total number of data points are the sum of those three. The sum squared between columns is you take A minus G squared times NA plus B minus G squared times NB plus C minus G squared times NC. Add it all up, I get sum squared between columns. Then the mean sum between columns is this number divided by k minus 1 divided by 2. Gives you 21. Mean sum within columns. I take each A minus the mean of A take that and square it. I get all these numbers. Add them all up. I get the sum of AI minus A bar squared. Likewise for B. Likewise for C. Add these together. I get the sum squared within columns, 63. Divide by n minus k. 24 minus 3. Divide by 21. I get 3. Means sum within columns. The F score then is the ratio of these two, 7.25. That's called analysis of variance table. This is something they do in business. In the College of Business, if you want to calculate this, you go through this table, grind out all these numbers. This is equivalent to this MATLAB code. So on your homework sets, you can do it either way. Run this MATLAB code, build the analysis of variance table, same thing. If you take other classes where they do analysis of variance, they probably use this table, but they're equivalent. And that's kind of what this goes through, the steps. I start with the data in yellow. Here's my raw data. Then calculate the means, global mean, number of data points, find the total number of data points, compute the sum squared within columns, find MSSB, like I just described. Go to the right-hand side, over here in pink. Compute the distance to the local mean squared, find the total, add them up, find mean sum within columns, compute the F score. And again, one of my pet peeves is if you're going to go to all this work, I've got the data. Why don't you just take each data point relative to the global mean squared, that's the true mean sum between columns. So you don't have to do this approximation. But again, that's not how analysis of variance is done. If you do it that way, in my opinion, it's correct, but it's non-standard. So let's have some fun with analysis of variance. If you go to Hector Airport, data's also on Bison Academy, it's got the average temperature in Fargo since 1942. And here's what it looks like. Let's do analysis of variance to compare the 50s versus the 60s versus the 70s. Are the means the same? Well, what I do is I take my data. It's got a mean, standard deviation, number of data points for the 50s, 60s, and 70s. And if I plot those as a normal distribution, this has the same mean, same standard deviation for the 50s, 60s, and 70s. Are the means basically the same? Well, to do that, I would input the data into MATLAB. Here's the first, data points 9 to 18 are the 50s, 60s, and 70s. Find the mean and variance of each data set, number of data points for each data set, the total number of data points, the global average, the mean sum between columns, mean sum within columns, the F score, and here's what you get. We've got 30 data points. The global mean is 40.49 degrees Fahrenheit. Mean sum between columns is 0.6. Mean sum within columns, 2.96. The F score is 0.2. An F score less than 1 is nonsense. The reason I got that is this number is just approximate. If I were to take all the data together and find the variance would be bigger than MSSW. Then the F score would actually be greater than 1. Less than 1 is kind of nonsense. What this tells you is that there's basically no difference in the means. So nothing was really happening between the 40s, 50s, 60s, and 70s. So just as kind of a sidelight, in my opinion, this is the correct way to do analysis of variance calculations. What I really want is the numerator to be the mean sum within between columns. What is the sum of the data points relative to the global average squared, divided by the sum of the data points relative to the local average squared. So the correct way to do MSSB would be, if I have all the data, just add up the distance of each data point relative to the global mean squared. Do that for A, B, and C. then divide by n minus 1. So I have n data points, 1 global mean, n minus 1. That's mean sum between columns, 0.0147. The mean sum within columns would be the same we did before, divided by n minus k, 0.0133. Take the ratio. Now the f-score is 1.1056. Going to StatTrack, I have 1.1056 for the f-score. The numerator has n minus 1, 29 degrees of freedom. Denominator has n minus k, 27 degrees of freedom. Calculate the probability, and it says 60% chance. So the correct score would be 60% chance that the 3 decades have a different mean. That'd be the correct way of doing it. Problem with that approach, in my opinion, that is the correct way of doing it, but that's not the standard way of doing it. If you do it this way, people will get confused, not know what you're doing, even though the answer is the correct answer. So maybe do it this way, maybe not. Anyway, that's kind of a sidelight. The correct way of doing it, in my opinion, if you have the data, you might as well do it the correct way. But carrying on. So anyway, okay, so it looked like the 50s, 60s, and 70s basically have the same mean. What that tells me is that from a climate standpoint, really not a whole lot of difference. Well, let's try that again. Let's compare the first 10 years, the 40s, versus the 80s, right here, versus 2010s. Those 3 decades. Do those have a different mean? Well, again, you have your data. I would pull in those data sets. Each data set has a mean, standard deviation, number of data points. So here's the 40s, 80s, 2010. Now it sure looks like it's getting warmer. That's what it looks like. Does it show up in the data? So let's do analysis of variance in this case. I can set up an analysis of variance table. Here's the 40s, 80s, 2010s, mean of each data set, global mean, number of data points, total number of data points. This is A bar relative to G squared plus B bar minus G squared plus C bar minus G squared times NC. It gives you the sum squared between columns divided by k minus 1 divided by 2 gives you 25. Mean sum within columns. Take these data points minus the mean of A squared. Likewise for B, likewise for C. Add them all up. I get the sum of AI minus A bar squared, which is also the variance of A times NA minus 1 times 9. Variance of B, variance of C. Add these numbers up. I get the sum squared within columns divided by 27. 30 data points minus 3 columns, 4.6. Take that ratio, that's the f-score. F-score is 5.5. Equivalently, I can use this MATLAB code, pull in the data, calculate the means, variances, total number of data points, mean sum between columns, mean sum within columns, f-score, and I get the same answer. To convert that to a probability, I use an F-table. The numerator has 3 columns, meaning 2 degrees of freedom. Denominator has 30 data points in 3 columns, meaning 27 degrees of freedom. My F-score is 5.5182. Probability then is 0.99. So I'm 99% certain that the climate is changing. Again, the F-score, F-test, doesn't tell you which direction it is. It just says the means are different. So something is changing. It was pretty consistent back in the 50s, 60s, and 70s. More recently, it has changed. That's an F-test. So in summary, an F-test is a way to compare 2 variances. For example, if I have 2 batches of resistors, are they different? We could also do that with a 1K resistor. I measured a 1K resistor and the variance was like 3.2. If it was uniform distribution, the variance would be 28. Take the ratio, I can tell you why the variance is different. Yes, they are. The reason you want to do that is if the variances are different, this will tell me that the distributions are different, or typically in industry, a change in the variance indicates the manufacturing process is about to fail. Analysis of variance is a slightly different type of F test. This is to measure 3 or more populations and tell me if the means are different. It doesn't tell me which one's different. I need to use a t-test to figure that out. It just says, are the means basically the same or are they different? If they're the same, like I've got 3 vendors sold me a transistor. If all 3 vendors have the same variance or have the same means, basically throw them all together, call it one big bin. If they're different, then I know I probably shouldn't throw all those transistors together. They have a different mean. The analysis of variance results in an F test, and a large F score indicates the means are different, meaning the data came from different populations or something's changing in the system. T-test is then needed to find out which population is the outlier. So that is lecture number 31 for ECE 341, F test and analysis of variance.